We had mentioned that there were two intramolecular bonds. We just talked about ionic bonds, how they form, and kind of properties that they might give. We'll talk about a little bit later on. But now let's look at the second type of intramolecular bond, and that is covalent bonds. Now, biology is a language, and like any language, if you want to be able to speak and understand it, you need to learn the words. It's just that there is so much vocab in most biology courses. That's why it's very, very important to learn the technique of breaking down the words and figuring out what they mean. So just like an ionic bond is formed based on ions, a covalent bond can also be broken down. Let's look at the word first and see how we can break it down. Covalent. Actually, it tells us an awful lot about what the bond is and how it works. The word co implies cooperation, sharing, working together. Okay? And valent describes the number of electrons in the outermost field. So it's literally telling us that they're going to be sharing some electrons in their outer fields. How does that happen, and why don't they do something like an ionic bond? Why do they end up sharing? Well, let's look at an example. And the example we're going to look at is a molecule you should be very familiar with. Take a deep breath, because it's time to look at oxygen, O2. Okay, now oxygen O2 forms a covalent bond, and here's how that happens. We know that the atomic number of oxygen is 8. Okay, and what that means is it has 8 protons and it has 8 electrons, assuming there is no charge. So let's go ahead and draw ourselves an atom of oxygen. Let's put a nucleus in there, and inside that nucleus, of course, we have the protons and the neutrons. Around that we have the electrons, 2 in the n is equal to 1 orbital, and the remaining 6, 1, 2, 3, 4, 5, 6, are in the outermost shell. Okay, so here are our 1, 2, 3, 4, 5, 6 valent electrons. Obviously, if we're going to be drawing a covalent, we're going to have a second oxygen atom, and it's going to need to overlap the first one, especially on the outer shell. Okay, so let's go ahead and draw the second oxygen atom. There's the nucleus. Here is our n is equal to 1 shell, and the second shell I'm going to draw it overlapping this first one, so it looks a bit like a Venn diagram. Okay, and that's what it looks like, boys. It doesn't look like anything else. It looks like a Venn diagram. Okay, so what about these 6 valent electrons here? Well, I'm going to go ahead and put 2 in the shared area, and in a moment I'll explain how we know that it is 2. So here's the 2 from the second oxygen atom joining the first 2 from the first oxygen atom, and the remaining 1, 2, 3, 4 electrons, bringing the total of 6, are in the other part of the shell. Okay, so now we have 2 oxygen atoms. Now you might be asking the question, right, but how did you know how many electrons to put into the shared area? Well, it's quite simple. Oxygen has a valency of 6. It wants to have a full outermost shell. It wants to get to 8 electrons. The quickest way to get from 6 to 8 is to plus 2. Therefore, they would need to share 2 electrons. If both oxygen atom A and oxygen atom B donate 2 electrons to this overlapped shared area, then effectively they both have 8. 4, 5, 6, 7, 8. 4 in the middle, and 4 belonging to each oxygen atom independently. Now you might say, why wouldn't they form an ionic bond? Why wouldn't oxygen atom A simply donate 2 electrons to oxygen atom B? Well, that wouldn't make oxygen atom A very happy at all. It would go from having a valency of 6 to a valency of 4. And that's no closer to its ultimate goal of being full or empty in its outermost shell. So, and it's, well, on top of that, oxygen atoms are equal. They have equal electronegativities. That means they attract electrons, I beg your pardon, with an equal pull. So covalent bonds are going to form like this. Now, this particular covalent bond is a non-polar covalent. And a molecule that is polar would have a plus charge on one side and a negative charge on the other. Now these 2 oxygen atoms are of equal size, and that means they're pulling the electrons equally. Well, if you're pulling things equally, then nobody has more of a negative or more of a positive charge. So when we have 2 atoms that are of equal size, they form a non-polar covalent bond. Let's look at one more example of that, and we're going to look at H2. Okay, and that is hydrogen. In order to draw hydrogen, we need to remember the atomic number is 1, so that's 1 proton and 1 electron. There it is. Let's draw the second atom over here, and as always, I'm going to need to do an overlapping. That's a rather big orbital, and we're going to put the second electron in here. Again, how do we know how many electrons to put in the shared area? Well, the valency is 1. It wants to have 2, given that n is equal to 1 has a maximum capacity of 2 electrons. And so that would mean to share 1. It's the difference between the valency and the full outer shell that tells us how many electrons will be shared. And again, this is a non-polar covalent bond. How do we know it's non-polar? Well, these two atoms are of equal size. Okay, so let's look at a polar covalent bond next. Okay, so polar covalent bonds. How are they different to covalent bonds? Well, of course, they have similarities in that they are still sharing electrons, but the way they're sharing those electrons is going to be a little different, and that's going to lead to the polarity of the molecule. So polar covalent bonds, let's have a look at that. And by far the biggest and best example that we're going to have is probably the most important molecule to life, and that is water, H2O. Okay, it's a little bit more complex here. We're going to have 3 atoms cooperating and being covalent. Let's have a look at how that works. So let's go ahead and draw our oxygen atom first. And remember from the previous thing, we have our nucleus, and we have 2 electrons in the n is equal to 1 orbital. And let's draw our n is equal to 2 orbital. We're going to have 1, 2, 3, 4, 5, 6 electrons in there. Okay, now for hydrogen, well, remember it has a valency of 1, so it's going to want to share 1 electron. So let's make the overlapping field over here. We're going to share an electron with oxygen. That means this hydrogen atom now has a full complement of 2 electrons. And the oxygen just got a little bit closer in that it now has 7 electrons. In order to have its full shell, it's going to need to have a bond with a second hydrogen atom. And again, we're going to put another electron in there. Now again, if you're trying to figure out how many electrons to put in the shared area, simply look at the valency and then the number of electrons that it would need to add or take away from that valency, add to that valency to get to a full outer shell. So for oxygen, that was 2, and for hydrogen, that was 1. So 2 hydrogens can share with 1 oxygen atom. And here we see it is covalent. All 3 molecules have a full complement of electrons in their outer shells. Now, why do we call this a polar covalent molecule? Well, let's not forget that opposites attract, positives and negatives. And the nucleus of oxygen here is a lot bigger than the nucleus of hydrogen. There's a lot more protons inside the oxygen. So these electrons are going to be pulled a little bit closer to the oxygen atom. Okay, and that gives the oxygen atom a slight negative charge. Okay, one of the electrons from each hydrogen atom is being pulled a little closer. Okay, it's not that it's become an ion. It hasn't completely owned that electron. It is sharing that electron. But it's like, well, I guess it's like a big brother sharing with a little brother. Okay, when my mom used to give us stuff and I had to share it with my younger brother, I would often share quite equally. 1 for you and 2 for me. 1 for you and 2 for me. Or if we were asked to share the TV remote, we would have to put it between us, but it would always be a little bit closer to me because I was bigger. Now that's a terrible thing to do, but it's also part of nature. And we can see that here with these atoms. This oxygen atom is pulling the electrons closer, which of course means the hydrogen atoms are going to be relatively positive. Do not confuse this with ions, okay? It's not that the hydrogen atom has lost its electron, it's just that it's a little bit further away than it was before, so it's a partial charge. And this is why we call the molecule polar, because we have a negative end, which is the oxygen end, and we have a positive end, which is the hydrogen end. Okay, this is very, very important when it comes to our next objective when we start talking about properties. So let's just do a quick recap of our intramolecular bonds. We had 2 types. That was ionic and covalent. In ionic bonds, we have a metal and a nonmetal, and a transfer of electrons. So we end up with a cation that loses an electron and an anion that gains an extra electron, I beg your pardon. And it's the attraction between this cation and anion, attraction between the positive and negative, that's holding the molecule together. Very, very strong intramolecular bond. When it comes to covalent bonds, we know that they are sharing electrons. And they can either do that equally, as in a non-polar covalent bond. The examples we had were H2 and O2. And this is because those atoms are of equal size, they have an equal pull on the electrons, therefore nobody gains a positive or negative charge. And we can compare that with a polar covalent bond. In a polar covalent bond, one atom is much bigger than the others. Our example was water. Oxygen is a much bigger atom than hydrogen's. And so when they're sharing electrons, oxygen, just like that bigger brother who's being unfair, holds it a little bit closer to itself. It's a little bit more selfish with those electrons. And so it takes on the negative charge. And the smaller atoms take on a positive charge. Because they haven't given up their electrons completely, we can't call them ions, and so we describe the molecule as being polar covalent. And that's an important property, particularly that word polar. So we'll see that again in just a moment.